Welcome everybody to the 11th lecture of Differential Privacy. We are in the section of the class on differentially private machine learning, and today we're going to be talking about, I guess, two more algorithms on differentially private machine learning. Again, on the logistic note, for your project, the project proposal. Like many of you submitted your project proposal late, so I understand that there might not be enough time to make any progress from the proposal time to the midterm time. So I'm extending that for a week, and I'll update the milestones and also the things on the grid scope by a week. So you'll find a placeholder like later today, and I'll try to provide feedback to all the project groups today or tomorrow. All right. So in the last lecture, we talked about something that we can actually run in practice, even if the hypothesis class is very large. So these are the family of problems called convex empirical risk minimization problem. And we studied two algorithms, the output perturbation and the objective perturbation algorithms for this convex ERM tasks. Let's go over the setting, because today we're going to be using the same setting and discuss a family of new algorithms for this problem. So in the convex ERM setting, so we got the data that are often feature label pairs that are sampled IID from some distribution. From the perspective of differentially private algorithm, this is a fixed data set, right? So we're not relying on the distribution of the data for anything, but the distribution of the data is a kind of assumptions that people make for analyzing even the non-private version of the ERM, and for us to study the generalization properties of learning algorithm. And in convex empirical risk minimization problems, the loss functions, this L, is assumed to be convex with respect to a parameter of your predictive model theta. So theta can be, say, your weight, your vector of weight coefficients, or the concatenation of all the neural network weight matrices, and so on, that leads to the prediction given an input X. And then this loss function is going to compute the similarity and consistency of the predicted label and the actual label. And what this requires is it is convex in this first argument. And since now that this is convex, we know that we know that all the optimal solutions are grouped together in a convex set. And in particular, if this is strictly convex, then we know that the optimal solution is unique, and it is completely characterized by the equation that gradient is equal to 0. So in this case, yeah, we're defining this loss function to be this L of theta, and the gradient L of theta equals to 0 describes the optimal solution theta star. Yeah, this is a property of a convex optimization problem, and two of the common additional assumptions that we make about these functions are the Lipschitzness and smoothness of these functions. In particular, we assume that this individual L is L Lipschitz and beta smooth. These are non-negative non-negative constant that describes this loss function. In particular, when L is logistic loss, L is logistic loss, binary logistic loss, and then it is one Lipschitz and one force smooth for if one force smooth and one Lipschitz if this is logistic regression, the logistic regression, if the input X is bounded by 1, right? Otherwise, the smoothness parameter and the Lipschitz parameter will be scaled by the size of the input space. Okay, so you might need that for the last question of the second homework. So for this problem, we consider two algorithms, and the first of these two is the output perturbation. So this is an attempt to try to use what we have already learned, the Laplace mechanism and Gaussian mechanism to release the output Fitted coefficient theta star. We've seen that this theta star is not stable on its own right unless we make additional assumptions or unless we algorithmically enforce the stability of the output. So what do we mean by the output? The output is theta star equal to arc mean of this L theta. So when L is just all we assume about L is that it's a sum of convex functions, then there's nothing we can say about. Suppose we replace this L with L tilde, which comes from a neighboring data set by adding or removing one individual. What's gonna happen? From theta star to theta star tilde, the changes can be arbitrarily large. So for this reason, we define this regularized objective function and the regularized output, which makes things more stable. And the difference is that we're adding an additional regularization term that makes the objective function strongly convex. And thanks to the property of the strongly convex, we've seen that theta star lambda minus theta star lambda tilde, this is smaller than lambda, and then the gradient of this additional data point that we add or remove from this objective. So this will be theta right, and this is by our condition of Lipschitz properties, this is smaller than L over lambda. Okay, so this is something useful, and the argument to obtain this is simply by applying the optimality of theta star and the fact that like this objective function now satisfy lambda strong convexity. Okay, so by the first order condition of strong convexity, and then we add the two things up, and then by moving things around, we can obtain this stability bound. So to say it differently, this is a global L2 sensitivity of the optimal solution. And using this calculation, we can just apply the standard Gaussian mechanism by adding noise with to every coordinate of this theta star with magnitude, with a sigma proportional to say L over lambda epsilon 2 log 1 over delta, 1.25 over delta, assume epsilon is smaller than 1, and this gives us epsilon delta dp. Okay, so we also went on to analyze the utility of this output perturbation algorithm. And last time we used the smoothness property of this loss function L, but then I missed an exponent. So there's a small error in the derivation from last time, which affected the rate on n and all the other properties, which I'll do it again and make sure that it is correct and clear now. And I'm also gonna reanalyze output perturbation under the weaker condition of only the Lipschitz property, rather than assuming both the smoothness and Lipschitzness. Okay, so let's try doing it again. So under smooth loss, so let's assume that these loss functions are beta smooth. So what we can do is to simply make use of the property of this loss function being smooth. So let's just do this Taylor expansion and apply the definition of beta smoothness and plug in theta p, which is the optimal solution that we get from which is a solution that we get through the output perturbation, and then we're gonna on the right-hand side, we're going to use the optimal solution of the regularized objective function. Okay, so we'll have theta hat p plus half lambda theta hat p square. So this is smaller than L of theta theta star lambda plus half lambda theta star lambda square. And on the right-hand side, I'm like the cross term is 0 because the theta star lambda is the optimal solution for this objective function. So all I'm left with is half beta minus theta hat p square, right? And this is exactly the noise that we add. This is exactly the noise that we add, and we know that with high probability, the last term is bounded by some, with high probability, the last term is bounded by half beta times sigma square times d and times this residual term, which is 2 log 2 log d over rho, right? And with probability 1 over rho. I'm gonna ignore this part of the bound, like since it's just going to be trailing there and have nothing to do with the rest of it, so that I can keep the result slightly cleaner. Okay, and now the next step is to handle the additional regularization. So by the optimality of this theta star lambda, then we can just replace this with theta star. And then write the same inequality, right? And sigma square d, and I'm gonna group everything in the log by just writing this log and a dot inside. Okay, and this is by the optimality of theta star lambda on minimizing this this regularized objective function, and once we have this, and we are already ready to substitute we are already ready to substitute everything that we have, because this is larger than 0, right? So the left hand side is this, and the right hand side is what we want. This is the non-private optimal solution, and these are the 2 trailing terms, these residual terms that we want to take care of. Right, and the idea is that we want to choose this lambda parameter optimally such that it minimizes the right-hand side of the bound. Right. So what is that choice? For this, we need to substitute in the parameter delta. Parameter sigma, and this is half beta d, and this is sigma square. So just now we've seen that the global sensitivity of this is L over lambda. So we'll have L square, lambda square, epsilon square, and 2 times log 1.25 over delta, and this additional log term. Okay, so you yeah, so yeah, I guess there isn't this square root here, because yeah, otherwise it doesn't make sense. So you can see that we have this lambda on the numerator and then lambda on the denominator with a square, and all it remains for us to do is to minimize the sum of these 2 by choosing this lambda optimally, and by doing that we get choose lambda optimally to balance these 2 terms, and then we'll get theta star yeah, so let's first write it out. Yeah, there's something that I didn't take care of, but yeah, so let us first finish this part. If we balance these 2 terms, and we'll get this n to the power of 1/3, and this is because this is not actually beta smooth. This is actually beta n times beta smooth, because L is equal to sum of this individual Li, and each Li is beta smooth. In addition, like we're actually doing the smoothness expansion of this regularized objective function. So after we add this half lambda theta square term, and the smoothness term is also bigger by a fact by an additional constant of half lambda. So instead of having beta here, what we should actually have is n times beta plus plus lambda. So this is n plus beta plus lambda. So this is the smoothness property of this L plus this additional regularized term. So this is a smoothness property of the smoothness constant of this regularized objective. Okay, so because of that, so we need to patch this argument over here. So instead of having just beta, now we have n beta plus lambda everywhere. So now we're going to handle the n beta term and lambda term separately. So assuming the case when n beta term is large, then we can subsume this lambda inside this n times beta, and for which we can balance this two term and then get this n to the power of 1/3, d to the power of 1/3, beta to the power of 1/3, L to the power of 2/3, epsilon to the power of 2/3. And in addition, we will have this optimal solution, theta stars norm 4/3, and plus this additional log factors. 1/3. So that's the term that suppose if n beta is larger than lambda. What happens if n beta is smaller than lambda? Then in this case, like this lambda term would dominate, and then the kind of right choices for this parameter is going to be different, right? So when this happens, what we'll have is lambda over 2. This term remains the same, and on the right hand side we'll have on the last term on the right will be lambda will be lambda and lambda square, and these two got canceled, and you have one lambda. You have only one lambda in the denominator, and L square and D and everything else, and then all these log factors. And when you balance these two terms, you get the square root of everything as a product, right? So when you choose lambda optimally, instead of getting this n to the 1/3 over epsilon to the 2/3 term, you'll get square root of n. You get square root of n epsilon and square root of d L and log of that. Yeah. So whether or not like which term is large really depends on the relative difference between n times beta plus lambda. So usually n times beta is much larger than lambda, but for very smooth problems, for some problems that are nearly linear, and it might be the other way around. Okay, so that's that's our conclusion for the smooth losses for the objective perturbation, and for the Lipschitz losses, if we don't want to make assumption that this beta is bounded, then we can actually also obtain a utility guarantee for the objective perturbation algorithm. So what we can do is to simply apply the optimality of lambda theta star and the Lipschitz property of this loss function itself. So L of theta, this is our output, the private output, minus L theta star lambda, and by the Lipschitz property, so we know that each individual L is L Lipschitz. Therefore, the n times the sum of n copies of this Li is going to be n times L Lipschitz, right? So we'll have n times L, and then difference of the norm between these two. But again, like this is the noise that we add to the output, and then we can bound this. So first of all, let's add this additional regularization, and then use the fact that theta star lambda is the optimal solution of the regularized objective function. So we can bound the first term with that of the unregularized objective function plus this additional regularization term. Okay, and for the last term, we'll substitute the high probability boundedness of the noise as we've seen earlier. So we'll have n times L, and the magnitude of the noise is square root of d times L lambda epsilon. So notice that this is without the square. So therefore the scale is just a standard deviation of the noise, and 2 log 1.25 over delta. And together with this additional log term, like d over rho, right? So yeah, these are just log factors, and we've seen that whenever we have this lambda on the numerator in one term and lambda on the denominator in the other term, we can choose lambda optimally to balance to minimize the sum of these two, and this is plus this in the order of I guess square root of n over square root of epsilon d to the power of 1/4 L, and then this log factor to the power of 1/4. Okay, and that's the kind of yeah, that's the kind of bound that we get in the end for the Lipschitz loss functions. So notice that this grows with n, but like I said, there's no big deal because the original loss function is proportional to n. So dividing both sides by a factor of n, you still get something that goes to 0, and therefore the bounds are non-trivial. It's better than just output some random random theta and then get perfect privacy. Okay, yeah, so it turned out that the analysis of output perturbation, even for a simple algorithm, when the privacy analysis is quite straightforward, the utility analysis requires us to make use of convex optimization and many by putting together many of these inequalities. Though it's still kind of like an easy argument because it just everything follows through by applying all the conditions that we're willing to make. And the stronger condition that we're willing to assume, the stronger bound that we get, and the weaker condition that we're willing to assume, then we still get something non-trivial, but the rate is slower comparing to the version where we make strong assumptions. So this is always going to be the case. Yeah, without assuming anything, usually we can't like prove anything. It is like an art to think about what are the assumptions that are reasonable, and what are the assumptions that you can justify with practical examples that people use every day. Okay, and the second algorithm that we talked about was the objective perturbation. Objective perturbation, instead of adding noise to the output, it perturbs the objective function by a random linear loss. And this B is drawn from IID Gaussian distribution with a noise parameter sigma square. So you can think about this as adding a synthetic data point B and associated linear loss to this objective function. And this the noise that we injected to the objective function induces a distribution of the noise in the output, right? So for objective perturbation, the privacy analysis is more interesting than the objective perturbation because it requires us to work with a KKT condition and the just optimality condition, which says that the optimal solution theta hat p satisfy this plus, yeah, ignore this r, lambda theta hat p plus b is equal to 0. And by moving things around, we can establish a relationship between the realized value of this noise vector and the final solution that we get, theta hat p. And it turns out that this mapping, like in the strongly convex case, is a bijection, right? So the distribution of this B is IID Gaussian, and this is a transformation of this IID Gaussian by by moving some part of it bigger and some part of it smaller, but at the end of the day, it is still a distribution that's induced by ID Gaussian. So if the idea of the underlying proof of the privacy analysis is to bound the kind of the transformation between these two by bounding the log determinant of the Jacobian. And the privacy analysis involving like working out the privacy loss random variable, and then analyze the tail of the privacy loss random variable. So the kind of bound that we got in the end is something like this. So we get the privacy loss random variable is larger than, for the generalized linear model case. So this is 2 beta over lambda, like under the assumption that lambda, so this is actually log 1 plus beta over lambda. So under the assumption that lambda is much larger than beta, then we can get that this log term is proportional to log 1 plus x, and it's proportional to x. I'm adding this factor of 2 in front just to signify this. So assume lambda is larger than beta. Okay, and well, so that's the first term, and the second term is this L square over 2 sigma square, and the third term is sigma L square root of log 2 over delta over 2 sigma square. So as we can see that the last two term is very similar to that of the Gaussian mechanism. So we try to bound the tail of the privacy loss random variable. So we can treat it in a very similar way to that by making sure that this is epsilon, and then this algorithm will satisfy epsilon delta dp. In particular, if lambda is larger than epsilon over 4 times beta, then we can the way we choose this is to ensure that for the first term is half epsilon, right? So all we have to do is to choose a second and third term together to satisfy half epsilon, to have a half epsilon upper bound. And using the classical Gaussian mechanism, we can choose this sigma parameter. So notice that this sigma cancels with this square sigma in the denominator. We can choose this sigma to be proportional to, again, to the global L2 sensitivity that is that is L or epsilon over 2, because we want to calibrate to epsilon over 2, and square root of 2 log 1.25 over delta, and this suffices to give us a high probability tail bound of delta at this value. And then the second term is half epsilon, and the first term is also half epsilon. Altogether, it gives us an epsilon upper bound of this tail probability. Okay, for the more general smooth learning problems, the result that we get was slightly good that I catched it. Because laptop like wasn't being charged. Okay. For the smooth learning problem, we have a slightly weaker bound for the last term that we got. So just to give you a little bit more intuition. So the first term is coming from the log log determinant. So this is coming from how much difference that log determinant factor is when we switch from one data set to its neighbor, right? And this gives an upper bound of that. And the second and third term handles the part of the Gaussian, the ratio of the Gaussian density that is directly coming from the distribution of the normal distribution of this B vector, right? And the special property of the generalized linear model allows us to reduce the problem of bounding the ratio of two multivariate Gaussian inner product with something dependent into a univariate Gaussian problem. Like hence this much nicer expression. But in the general smooth learning problem, we cannot actually do that. So the type of bound that we get is slightly different and worse by some dimension dependence. So the first term is now 2 times d beta over lambda. The second term is actually the same, but the third term now has this additional factor of d, square root of 2 log d over delta, right? So this d and that d, so these are in addition to what we got for the generalized linear model, but this is something that we can show by just using a weaker bound that takes care of the dependence in the last term of the privacy loss random variable. And if we just use the same do the same calculations and then handle both terms separately by setting this part to be half epsilon and setting this part to be also half epsilon, then we can get epsilon delta dp. The corresponding choice of lambda is basically just needs to be d times larger, and the corresponding choice of sigma also needs to be larger by a factor of d. So this will be d. Yeah. So that will ensure that both terms are smaller than half epsilon. Yeah, I think I missed this factor of d in the log, but yeah, that doesn't matter that much. Okay. So in this lecture, what we're going to do is to start with a utility analysis of the objective perturbation, right? So just now, this is a privacy analysis, which tells us how much noise we need to add in order to achieve this epsilon delta differential privacy. And now we're going to analyze this algorithm to show that like what is the kind of correctness that it obtained relative to output perturbation, and in what cases it is better than output perturbation, in what cases it is not, right? And the utility analysis will also reveal some limitations of this family of approaches in working directly with the optimal solution and then trying to deal with the optimality condition and try to prove things. So then that will motivate us to consider another family of algorithms that are more incremental, that tries to like privatize every iteration of a particular algorithm, and then at the end of the day, it will obtain like some more interesting properties than what we are able to get from output and objective perturbation. Okay, so that's the plan for today's lecture. For the part of objective perturbations, utility analysis, and so on, I'm still referring to the Chaudhary et al. And Kiefer et al. You can see that the details from the last lecture. For the part where I'm going to be talking about the noisy gradient descent and noisy stochastic gradient descent, the materials that I'm drawing those information from is scattered all over the place, but you can find the good material for the noisy SGD algorithm, which obtains the information theoretic limit for differentially private empirical risk minimization in a convex setting from this very nice paper by Riff, Basilia, and co-authors. Okay, so these are the additional information. Suppose you are interested in looking into this problem a bit more. Okay, so now let's start doing a utility analysis of the objective perturbation algorithm. Okay, so to start, let's define this regularized objective as J. Yeah, so that will save a bit of writing of lambda theta star. Okay. Well, so the analysis will go by first using the fact that theta hat p is a minimizer, right, of J theta plus B transpose theta. Right, theta hat p is a minimizer, so this is coming from the algorithm itself. Therefore, we can write this J theta hat p plus B transpose theta hat P is smaller than J theta star lambda plus B transpose theta star lambda, right? Theta star lambda is a minimizer. It's minimizer of this J objective function. Okay. Now we can move this term to the other side, right? We can move this to the other side, and that gives me B transpose theta star lambda minus theta hat P. Okay. And now following the same argument that we've seen before, we can replace this J with we can replace this theta star lambda with theta star, where theta star is the arg mean of L theta. This is arg mean of the unregularized objective function. We can always replace this because theta star lambda is the optimal solution, right? Plus B transpose lambda minus theta hat P, and this is L of lambda plus half lambda theta star, right? The same thing as we've gotten from the upward perturbation, and later we'll be balancing this term with like all the other things by choosing this lambda optimally. But for now, let's keep this here. Like now what we need to have is one way for us to handle this factor, this inner product. So what we're going to do is to just apply the standard Cauchy-Schwarz inequality by bounding this with the Euclidean norm of the difference and the magnitude of this noise. Okay, and it boils down to how we can do this, how we can bound the in some sense the perturbation of the objective function, the perturbation of the optimal solution after we perturb the objective function J theta by this additional like linear loss. But there is something that we know, right? There is something that we know about how we can do this, because previously we've seen that, like, recall J is lambda strongly convex, right? So previously we've seen that strong convexity implies the stability of the optimal objective function, the optimal argument that achieves the optimal solution. Right. So and what the kind of context that we apply this to is to analyze the global L2 sensitivity of the output perturbation algorithm. But the same logic would apply here, since since now without adding this linear term, this J is lambda is lambda strongly convex, and clearly this B transpose theta it is Lipschitz, right? It is Lipschitz by the magnitude of B, and because of it we can apply the same strong convexity and then bound the perturbation of these two values by this Lipschitz constant of B transpose theta over lambda, right? So this is applying the same stability lemma that we've got, right? And what is the Lipschitz constant of this? And this is equal to just the norm of B over lambda, which shows that this is which further allows us to bound this term and plus just 1 over lambda B square. Okay. Yeah, let's put this in a box. And then now we can apply the high probability bound of this noise vector. I know the noise vector is drawn from normal 0 sigma square ID, right? So we can bound its magnitude by bounding every coordinate or applying like a fancier inequalities that applies to the chi-square random variables, but by a simple Gaussian tail bound on every coordinate and the union bound, it will give us more or less a tight result. And then we can also substitute into the substitute in the value of the chosen sigma parameter. So this will give us lambda and what is a sigma square parameter here? So yeah, we've seen from previously. So sigma square. Yeah, we'll substitute this later, but let's first deal with log. So that you will have 2 log d over rho. So this holds with probability 1 minus rho. Okay, so now for generalized linear model, we can substitute in this particular sigma, and then the type of by the way, choose lambda optimally, and we can get L theta star plus just sigma this log to the 1/4. Wait. Okay, this is a square. So this is log square root of this log, and multiply with the theta star. Right. So this is this is what we will get. So it then remains to substitute the different choices of the sigma parameter for GL generalized linear model for the or the smooth learning problem. So if we substitute this value for the generalized linear model, we will get the square root of d L over epsilon 2 log 1 over delta, and then square root of this log additional d over rho term, right? And for general smooth losses, we get order of so recall that sigma is another factor of square root of d larger. So now we'll just get d L epsilon 2 log 1 over delta star, and everything else is the same. Okay, so that that handles the yeah, that handles the that handles the utility of the objective perturbation. There might be something that I missed, but let me take a look. I see. Yeah. So there's another thing that I might miss, which is coming from the privacy analysis of the objective perturbation. So recall that sigma is not the only thing that we require to do, right? So there's another condition that this lambda needs to be larger than epsilon over 4 beta. So this parameter, this condition needs to be satisfied. And for this condition to be, and this condition gives a feasible region for this lambda parameter. And when we optimize over lambda, we need to check that this condition is true. Okay, so I'm not gonna talk about this in details, but whenever we cannot actually choose the optimal choice of this lambda to achieve this bound, then it is a case that when we choose this quantity at the corner, then on the boundary, then it's gonna give us some low order term comparing to this rate that we got. So at the end of the day, so the kind of bound that we get for both cases will be the maximum of this, and the other one, which I guess the minimum of this, and the other one which requires us to take care of that boundary condition, right? So these rates apply under this additional condition that either beta is sufficiently small or lambda is chosen to be sufficiently large. But what makes this quite interesting is the last part of this analysis doesn't actually depend on the beta parameter at all. So this really just an additional assumption that needs to be checked. But this expression themselves doesn't directly depend on how strongly smooth this problem is. Unlike previously in the analysis of output perturbation, which explicitly relies on the smoothness parameter. So these bounds do not rely on the strongly smooth parameter, which says that even though we require the twice differentiability for this problem to hold in order to convert the distribution of the noise into the distribution of theta hat p, we don't actually need that much of a strong assumption on how strongly smooth and that have an impact in the final final sample complexity that we obtained in the end. Okay, as a checkpoint. So let's summarize the excess empirical risk of the two algorithms that we've learned: the output perturbation and objective perturbation. Okay. In output perturbation, we've analyzed it in the more general Lipschitz loss cases and the smooth loss cases. And in the Lipschitz loss cases, now that everything is normalized by 1/n, so that it is comparable with the kind of statistical rate that we have in mind. So in the Lipschitz losses cases, we get this rate, 1 over square root of n times epsilon. And if we, in addition, assume that it's beta smooth, then beta appears in the numerator, and we can get an improvement over the previous bound. Then you get n to the power of 2/3. And when we, in addition, assume that the problem is a generalized linear model, it doesn't actually make a difference for the output perturbation. For the objective perturbation, we can see that it doesn't apply to the Lipschitz losses at all, because the Lipschitz losses can be completely not twice differentiable, which breaks the assumption, which breaks the argument in the objective perturbation that requires us to use the change of variable trick to convert one distribution to another. For the smooth losses, on the other hand, and provided that these low order terms are satisfied, then we can get a much faster rate comparing to that of the output perturbation. So now this is 1/n. And in output perturbation, it's 1/n to the 2/3. And if we, in addition, assume the smoothness property and Lipschitz property is satisfied for a generalized linear model, then our objective perturbation gives us something that's more or less optimal. And we can see that it depends on square root of d, and this is over n epsilon, and this is also a lot faster than this. So one way to think about this is group this d square root of d over n epsilon together, right? And this one will be this to the power of to the power of 2/3, and this one will be d to the power of 1, right? So in the regime when n epsilon is larger than d, in any sense that the result is non-trivial, then this term dominate the result that you will get from output perturbation. Okay, but there are cases when the objective perturbation is just not applicable. Okay. Another remarks I'm going to make is that it's about how much additional cost that we suffer when we require differential privacy relative to the kind of statistical error that when you want to solve these problems for new examples, when you want to calculate the generalization error. So notice that this is access empirical risk. Suppose we compare that with the access risk, which is of the non-private problem. We can see that generally the access risk is on the order of square root of d over n, rather than d over n. So therefore, the objective perturbation is actually gives us something very appealing as it doesn't have really have additional dependence in d, and as epsilon is relatively large, in a reasonable range, the epsilon equals to 1. It gives us a much faster convergence comparing to the worst case non-private access risk bound, which is square root of d over n. Yeah, things becomes more complicated when we consider the fast rate phenomena in the non-private learning problems, which sometimes could make the non-private rate like d over n. And it depends on what these assumptions are. Sometimes they also have an effect on the private learning problem, but in other cases, they do not have any effect on the private learning problem, which means that for these more specialized structures in your learning problem, if they are true, you cannot actually take advantage of them easily with these algorithms, even if the problem is much easier. Okay, and the cost of privacy becomes relatively a lot higher. Okay, so far we've seen like 2 algorithms for convex empirical risk minimization, and their privacy and utility analysis. On the other hand, like they do not solve the full family of convex empirical risk minimization, because like sometimes all we want to assume is that these functions are convex, and sometimes we want these methods to naturally extend to the non-convex world. But like these 2 algorithms, clearly they rely very strongly on the convexity assumptions and on the fact that the loss functions are twice differentiable, yeah, for the objective perturbation at least, and there are convex losses that are not even differentiable. So take the absolute value, say, or the absolute value loss, which looks like this, right? So this is a convex loss, but it is not differentiable at 0. Right, and this is a kind of loss that gives you the robustness that's typically needed in learning. So like the techniques that we learned so far doesn't really handle this like very easily. In addition, we cannot handle the constrained convex optimization problem. So sometimes the type of problem that we try to solve is a minimize of this empirical risk. Scaled empirical risk. In addition, that say the 2 norm is smaller than some parameter b, right? Or there could be other constraints that encode the additional knowledge that you have about the problem. And so far, when we were using the optimality condition, we've been assuming that this region of feasible region is unconstrained, is R to the d. Therefore, we can simply take the gradient is equal to 0. But when there are constraints, like the condition for optimality becomes the full KKT condition, and that breaks some of the arguments in the analysis of these methods. It just become like not very scalable, because almost for every new problem, we'll have to somehow come up with this theoretical analysis and to work with their bounded constraint set in a highly specialized way in order to deal with it, and it's just not gonna generalize to this broader family of problems. And in addition, as I mentioned earlier, so one good characteristics of these popular machine learning algorithm, this optimization algorithm, is that even though for non-convex problems such as the training of deep neural network, we don't really have much to say about this theoretical guarantee, but these methods they do work in the non-convex world. so when we are minimizing the ERM problems, when the loss is non-convex, we can still run, say, stochastic gradient descent. And then it often works in practice, and then sometimes it gives us sufficiently good training results. So even though it doesn't give the optimal empirical risk minimizer. Okay, so for these reasons, we wanted to consider this more flexible family of algorithms that just generically minimize an objective function f of x. And the only assumption that we're willing to make is that these objective functions are differentiable. Okay, so for now, let's not worry about constraints and let's consider the unconstrained version of the problem. And for these problems, the gradient descent algorithm, like it's very straightforward. It starts from somewhere. It starts from some initialization. And then you just look at your local neighborhood. Let's see that you're skiing, and this is your little skiing avatar on the mountain, and you're standing over there, and you're very myopic, and all you can see is a terrain just next to you. And what you're gonna do is to find the direction that gives you the fastest descent, right? So this is the direction of the gradient, and you're gonna just move a little bit towards that direction and then reevaluate your situation and then do this again. So by repeatedly update your parameter, by moving towards the direction of the negative gradient with this learning rate. So yeah, I'm actually gonna be using a slightly different notation over here. So we'll be using f of xt and xt plus 1. Yeah, by moving towards the negative gradient direction with the learning rate eta t, until some kind of stopping condition is true, then this algorithm often works in practice that gives us something close to the optimal solution. And the idea here is can we just privatize this algorithm rather than privatizing the optimal solution of privatizing the optimal solution of an objective each particular objective function. If we can do this, then this algorithm would apply more generally. At least the privacy guarantee would hold throughout for any such problems we're interested in. So even if maybe we don't have anything to say about utility. Okay, so to compare running gradient descent on two types of problems, the convex problems and non-convex problems, here's the illustration. So what is drawn here are like the terrains that you're moving downhill. Like this is your skier, and suppose you follow the gradient descent direction. When the problem is convex, no matter where you initialize, your algorithm will always lead you towards the eventual optimal solution in the valley. Okay, in the non-convex problems, you can still run gradient descent, but the solution that you'll end up getting is going to depend on a lot of other factors, and particularly it will depend on where you actually initialize your problem. Okay, so when you are here, then you're going to end up in this valley, but when you are here, you're on a different skiing slope, and as you go down, you'll end up in a different region of the mountain. Okay, so yeah, we'll take a break for 5 minutes, and we'll resume on 2:06, and then we'll talk about some properties of this gradient descent algorithm, and then we'll try privatizing this algorithm by coming up with like a privacy and utility analysis of noisy gradient descent for differential privacy. Okay, I'll see you guys in 5 minutes, and we'll resume on 2:07. Okay, guys, it's about time, and let's continue with the lecture. Just now we were talking about gradient descent, and we wanted to come up with an algorithm, a differentially private version of the gradient descent algorithm, so that it can be applied more generally to these convex problems and non-convex problems that were not covered or covered, but it doesn't give us sufficiently good results by output perturbation and objective perturbation. Okay, so I'd like to first comment on like how these can be used to handle the various cases that were not covered by the previous algorithms. So the gradient descent algorithm itself, it seems that it requires us to assume at least the objective function is differentiable, right? But the thing is that for instance, in a convex but non-differentiable case, we can use an extension of the gradient descent called the subgradient descent or subgradient method, which says that suppose this is a function that we're minimizing, and when we are at a differentiable region, then we're moving towards the negative gradient direction like this, and there are no ambiguity. So we're just running gradient descent. But suppose you are say in this region, suppose you are over here. And suppose you're over here, and all you have to do is to pick anything that is within the so-called subdifferential of this function at this point, which is given by all the possible linearization of this function at this point. So all these directions are valid descent directions, and you can pick any of them. And that simple generalization makes this a so-called subgradient descent. So the algorithm is still straightforward. It basically updates the parameter by moving towards the subgradient direction, where this is so-called subgradient. And then that's it. When you choose this learning rate eta t parameters appropriately, this algorithm is going to work, and it converges to the optimal solution at certain rate, and it's known to be optimal for this family. And we also talked about constraint. So how does this algorithm handle constraints? So it is possible that if we move towards the negative gradient direction, it will move us outside the feasible region, right? Say there's a feasible region that looks like this, and if we are here and the gradient is this direction, then we move a little bit towards this direction, and this is a new point, and that's fine. That's fine. We don't need to modify the gradient descent. But suppose you're over here, and the gradient says that you should move towards this direction. Then it is possible that you are this xt plus 1 will get you outside of this feasible region. So what you can do is to simply update the theta t plus 1 to be theta t minus eta t and the gradient or the subgradient gt. But then after that, you simply project it to the convex feasible region. And provided that this set is a convex set, and this algorithm is also known to work, and it gives you the same rate and same convergence guarantee as that of the standard gradient descent or the subgradient descent for the respective family. So in this case, it basically handles the constraint sets at ease without any additional issues. Yeah, so this projection is like whether this is computationally efficient, it depends on how complex these feasible regions are. But for the kind of constraint set that we typically consider, like like a Euclidean ball that we considered just now, or L infinity norm ball, or L1 ball, or the probability or the probability simplex, and so on, these projection operator can be done in either linear time in the dimensionality or log linear time in the dimensionality, right? So yeah, there are a lot of study on these projection operators that if we can generalize this algorithm, then all those information and all those existing algorithms are things that we can directly tap into. In addition, there are extensions to cases with a non-smooth penalty function. So what do we mean by a penalty function? This is this additional regularization term. So recall in the full version of the private empirical risk minimization problem, we are considering this problem plus this additional regularization, this R. This R might not be differentiable, even if this L is differentiable, right? So like our approach is to add this additional regularization, a square regularization on top of this thing that's possibly non-differentiable, right? And so what is the use of this R of theta? So this is often used to induce the type of structure that we know about the problem itself, right? So you can view this from the Bayesian point of view as this encodes the information of the prior, or you can view this as from the frequentist point of view by saying that these are the additional structure that I'm betting on to have a better bias variance trade-off. For instance, when this R is a L1 norm, then it induces sparsity, and that allows us to solve the high dimensional problems. And when this R, when X theta is a matrix and this R is a nuclear norm, then it induces the so-called low rank structure of the matrix, which allows us to like also handle the high dimensional optimization problem and high dimensional learning problems in a more efficient way, right? So being able to handle non-smooth penalty functions allows us to generalize the solution a lot more. But yeah, it wasn't like a priori handled because having this R of theta would automatically like make objective perturbation like not so useful because we can no longer use that Jacobian because this R itself is not differentiable. So in gradient descent, this is kind of straightforward. So instead of doing this simple gradient descent, so what we can do is to use something called a proximal operator, which is a generalization of the projection operator that moves towards just the gradient direction, and then do a prox with respect to this R, right? And then this serves as some kind of a smoothing trick that allows the same gradient descent analysis to apply while you are minimizing a composite objective function with a smooth term and a non-smooth regularization factor. Okay, so for all of these, you can yeah, you'll be able to find more information and more like interesting like insight and analysis on how these would work, like from my other class, convex optimization, which is offered on a like irregular basis. So sometimes it's on, sometimes these other graduate level courses are on. But convex optimization, whenever it is on, I do highly recommend everybody to take it. Yeah, it's might not be me who's offering it. Sometimes they are offering of convex optimization in electrical engineering, and sometimes in statistics. But the materials are definitely worth learning. And in addition, for the non-convex cases, like I said, like all these approaches that handles the using the projection and use the proximal operator, or it simply use subgradient. So in a convex case, defining subgradient is a little bit tricky. You have to define it to be so-called clock subgradient rather than the standard subgradient from Finchel et al. But you can still get it to work and then show some weaker theoretical guarantee. Say this algorithm will converge to a point nearest the stationary point rather than the actual optimal solution. Yeah, so in practice, like these gradient descent algorithms, they work remarkably well in non-convex problems, even though like we don't have much to say about them. Okay, so yeah, the next family of algorithm, which is actually the algorithm that we need to analyze in order to make it differentially private, is the so-called stochastic gradient descent. And the idea of stochastic gradient descent is motivated from the fact that sometimes n is very large, so the size of the data is very large, and to compute the gradient descent update in every iteration, you have to go over the entire data set, which is like not very scalable if your data set contains millions, if not billions of examples. So what stochastic gradient descent does is that it will come up with some kind of estimate of the gradient and then move towards the negative direction of that stochastic approximation of the gradient. And this G, this direction of your update needs to satisfy a number of assumptions. So first of all, it is required to be an unbiased estimator of the gradient. Condition on the this current iterate. Okay, so this is equal to the gradient of this function that you're minimizing. Secondly, it's typical to assume that in some senses the sum of the covariance, the trace of the covariance matrix of this G, condition on every input parameter is bounded. So the kind of assumption that we'll use over here is this G T minus the gradient of f theta T square. So this is a Euclidean 2 norm given theta T. So this is smaller than. So let me explicitly introduce a dimension here, like for the convenience later. Right. So these are the two conditions. So this says that it is unbiased, and the second condition says that it has bounded variance. Okay, so whenever we have these two conditions, then there are appropriate choices of this sequence of learning rate such that the stochastic gradient descent will converge in expectation and with a high probability to somewhere near the optimal solution. So the figure on the right-hand side, which plot the equipotential lines of the objective function in 2 dimensions, and it illustrates the difference of the standard batch gradient descent and the randomized stochastic gradient descent. So in blue, you can see that it is following. So in this case, you are skiing and you are always moving towards the actual direction that tends minimum, that is the steepest. So you'll move on this trajectory towards the optimal solution. On the other hand, when you do stochastic gradient descent, there is some noise. You're not necessarily always moving downhill. So sometimes you are moving uphill. Sometimes you are moving downhill. Sometimes you are moving but the reason why this algorithm could work is that in expectation it is moving downhill, right? So it is more random. But it could be faster because you don't need to stay there and then make the decision about which direction to ski to, right? And the benefit of stochastic gradient descent is sometimes you can construct this stochastic approximation a lot faster than actually evaluating the gradient itself. Okay. Yeah. So let me just on this page gives you an example of what is a typical choice of this GT. So GT can be constructed by the following. So again, so let's say that this f of theta is a sum over the individual loss functions, and this GT could be constructed by simply use n multiply with this L and then I of theta T. And this I is a random variable that is drawn uniformly at random from 1 to n. Okay, so why does this work? So we can simply calculate its expected value. Since this I is taking a uniform distribution, this becomes n times sum over from I to 1 to n, 1 over n. And then the individual gradient of L I of theta T, right? And by swapping the order of this summation and the constant multiplier, then we recover that this gradient is unbiased, right? And its variance would depend on the diversity of these data points, which we don't typically care that much about. So as long as this quantity is bounded, then we can come up with the right sequence of rate of eta that gets us to a near optimal solution. right? So you can see that this algorithm is a lot faster because it requires us to take only one data point uniformly at random rather than going over the entire thing. Okay, so by the time the stochastic gradient descent has gotten the near optimal solution, the gradient descent algorithm might have only moved for one step. Yeah, so let me summarize some of the known results about the gradient descent and stochastic gradient descent. And these will be useful for us when deriving the utility guarantees of a differentially private version of these algorithms. So it comes with like an assortment of different kinds of guarantees on the different assumptions of the problems. So we've already seen many of these assumptions. If we assume that this f that we're minimizing is smooth, so again we can call this, say, beta smooth. So yeah, notice that this is a different beta if what we have in mind of this f is the sum of these L loss functions, but f is beta smooth and convex, then it can be shown that the gradient descent algorithm after, say, t iterations from the initialization, so this is smaller than beta t minus theta 1 square over t. And this requires us to choose this learning rate. This requires us to choose this learning rate eta to be a constant at 1 over beta. Okay, so and for general convex problems that doesn't require smoothness, so it can be shown that so it's slightly more complicated, but let me try writing this down. Sorry, but the previous statement doesn't make sense because I've made a typo in it. This is like theta star. This should be theta star rather than theta 1. And on the right hand side, this is theta 1 minus theta star. Okay. Now this makes more sense, right? So and theta star is defined to be the arg mean of f of theta. Okay, so the left hand side says that this is a suboptimality. This is how, since we're minimizing this f, this is how far away that you are from the minimizer. You are away from the smallest possible value of this function. And on the right hand side, this says that as your number of iterations gets larger, and this converges to 0 at a rate of 1 over t. Okay, and t is the number of iterations. So for the general convex problem, when we are not making an assumption that f is smooth, but only that f is Lipschitz, then we can show that how far away that you are from the optimal solution, like throughout the throughout the iterations, is smaller than theta 1 minus theta star 2 nor multiplied with L. This L is f is L Lipschitz over square root of t. Okay, so for general convex problem, we have a slower rate, but it is still converging. It is getting closer and closer to the optimal solution in terms of the objective function value. How about the stochastic gradient descent? Like, do we lose something more? Like when we can only have access to the noisy version of the gradient information. So what we can get in the stochastic gradient descent is very similar to that of the gradient descent in the general convex problem, or subgradient descent in the general convex problem. So the type of result that we get is very similar. This is smaller than square root of L square plus d sigma square over square root of t. Yeah, so all of this is up to like universal constant of sometimes a factor of 2 or a factor of 4. And recall that where is this sigmas coming from? This is saying that the stochastic gradient that you get in every iteration minus its expected value, which is the actual gradient. This is condition on theta t. This is smaller than d times sigma square, right? So the additional stochasticity like comes as an additive term in numerator. So suppose we have noise, even though like this algorithm still converges, it doesn't affect the rate of convergence, but it affects a constant. It affects the number of iterations that it takes for you to get to the epsilon solution. Okay, so lastly, for strongly convex problem, let's say that f is lambda strongly convex. Then you can show that this this 1 to t. This is 1 to t. Right. For strongly convex, you can show a similar result. But a lot faster for the stochastic gradient descent. So what you can get is that you'll be no longer dependent on this boundedness or on the difference between the optimal solution and your solution. So what you end up getting is this L square over d sigma square over lambda times t. Yeah, what this is saying is quite nice, that the only thing that we can, they're all the same algorithm, but the only thing that we need to tune is a learning rate parameter. So if we tune the learning rate parameter appropriately, it can adapt to the strong convexity parameter that's coming from the problem itself, right? So this is not necessarily like what we added ourselves as in the previous analysis, but this might be coming from the sum of the loss functions themselves. If they satisfy strong convexity parameter, then gradient descent will converge faster. Stochastic gradient descent will also converge faster, right? So I'm skipping the part where the faster convergence of the gradient descent on this problem. Because it's like this is already 1 over t, and if you further assume strong convexity, the gradient descent will converge exponentially to the optimal solution. So it's a lot faster. And in addition, this 1 over t term for the smooth and convex problem is not actually optimal. So there's other gradient descent methods that's very similar to the gradient descent algorithm that will converge at a rate of 1 over t squared. So that's called the so-called accelerated algorithm. So there are a lot of those things that we know about how these algorithms work. And the last thing that I wanted to mention is that the projected version of these, they basically work without changing anything, right? So for all of these, when the update rule becomes the projected version of the update rule, and then all these rates remain intact. And you still converge to the same solution at the same rate, but now in a constrained optimization problem. Okay, so all of this is quite nice. So to give you a flavor of how these actually works, so I'm gonna like very quickly sketch the convergence of the stochastic gradient descent on a problem of the convex non-convex setting. So in a non-convex setting, so we can no longer hope to get some result that looks like theta t minus f of theta star. Like we can no longer bound this because there are multiple local minimas that we may get stuck. But what we can do is to show that the gradient descent algorithm or stochastic gradient descent algorithm will end up converging to somewhere that's nearly nearly a stationary point. So you'll converge to somewhere that is say flat. Let's say that you initialize the algorithm here, and it ensures that you will converge to this point. And suppose you initialize here, then like if it is sufficiently random, then maybe it will converge to here, or maybe it will converge to the actual global optimal solution. Right. So the kind of challenge in non-convex setting is about finding the needle in the haystack, because there could be exponentially many different like local optimal solution. And if you're stuck there, the local information can no longer tell you about whether this point is globally optimal. But for this reason, so let's make the let's make the requirement weaker so that we can say how quickly that the algorithm will converge. Right. To start, we'll use something that's also useful for analyzing the convergence of the gradient descent in a convex case called the descent lemma. So what the descent lemma says that so again, let me write down the update rule. Yeah, for this, let's switch to x, because writing theta is more difficult than writing x. Minus eta t, and then gradient of yeah, let's use g, since g is our approximate of the gradient. Okay, so that's the SGD update rule. And by the smoothness property, by the beta smoothness property, we can Taylor expand around xt plus 1. This is smaller than f of xt plus xt plus 1 minus xt inner product with the gradient of f at xt, and then plus this additional smoothness term, xt plus 1 minus xt squared. Okay, so that's the by the smoothness of f. And now let's substitute in the update rule. Okay, so if we substitute in update rule, we'll see that this is f of x plus the minus eta t gt gradient of f of xt plus half beta eta t square gt square. Okay, and now we can make use of the assumption that we made about the gradients, right? About the stochastic gradient. So recall that we are assuming that the expected value of this given xt, this is equal to the gradient. Right, so that's the first assumption. And the second assumption is the expected value of this gt from its expected value square given theta given xt. This is smaller than d times sigma square. Right, so these are the two assumptions. Now let's apply these assumptions by taking expectation, taking this conditional expectation on both sides. So the conditional expectation of f of xt plus 1 given xt is smaller than f of xt. This is not random because we're conditioning on ft. And the middle term will simply becomes eta t gradient of fxt square. And plus half eta t square beta. And when we take the expectation of these two and it breaks down to the square of its expected value. So basically I'm using the definition of the variance. So variance of x is equal to e of x squared minus e of x bracket square. I'm using this by moving this e of x squared to the other side, right? So I can bound the conditional expected value of this by the sum of this variance, which is something that we assume, and the square of this expected value. Right, so what I'm gonna get is gradient of fxt square plus d sigma square. Okay. Now let's make one assumption on the learning rate. Let's assume that the learning rate eta t, or let's assume eta t is equal to some constant eta. Okay, so that's the first assumption. And the second assumption, let's say that this is smaller than, let's say that this is also smaller than 1 over beta. Okay, smaller or equal to 1 over beta. if this is smaller than 1 over beta, then we can replace one of this eta t square on the right hand side with 1 over beta. So this becomes minus eta gradient of fxt square plus so I can replace this 1 over one of this eta t with 1 over beta, and that cancels with this beta. So we'll get eta over 2, 1 over beta, these two got canceled. And then I can break the terms in the bracket into two parts. Half eta d sigma square. Okay, and then these two both have the gradient differences, and this becomes f of xt minus minus half eta gradient of fxt square plus 2 d let's see that this is smaller than 1 over beta 2d eta. Sure. Okay. And now what this is saying is that, like, first of all, let's try substituting this sigma to be 0, and then we can see that what this says is that the objective function is always going to go down, right? And how much you will go down is proportional to to this quantity. And actually actually over here I'm gonna improve the bound a little bit for the last term. So instead of just having d eta, so I'm gonna have like d eta, the minimum of eta and eta square beta, because sometimes I might choose this eta parameters to be substantially smaller than 1 over beta, and you'll see why this is useful. Yeah, I can take the mean of these two. Yeah, in fact, let me just use this eta square beta. So I will be using this eta square beta sigma square for the second term, right? And I'm gonna use this eta term for this gradient one. So then multiply with d, and this will gonna save us some trouble later. So eta square beta sigma square d sigma square d over 2. Okay. Okay, so this is what we call the descent lemma. And the next thing that we're gonna do is to is gonna telescope and then show that this actually converges to something like a stationary point, right? So what we can do is to now take the full expectation on both sides, and what we will get is the expected value of f of t plus 1. This is smaller than the expected value of f of xt, and then minus half eta expected value of the gradient xt plus eta square beta square sigma square d over 2, right? What I'm going to do is to add up from 1 to t, right? So when I add up everything, then you can see that this differences in this like these objective function values, they will cancel out with each other. So let me see. Yeah, we still have one more page here. So this is fxt plus 1 smaller than e of fxt plus the minus the half epsilon expected gradient plus half beta square d sigma square. Okay, so I'm gonna add up all the t plus 2 now f of xt minus that. Okay, and so on. I'm going to add it all the way up to f of xt. F of xt minus 1 minus, yeah, so you can see that from the first item to the last item and this is plus 1, and this will cancel with that, and this will cancel with that, and this will cancel with that. And all we get, like now that we can group all this gradient together and move it to the left-hand side, and this gives us the t times the eta over 2 expected value of the sum of the gradient square, and this is smaller than expected value of fx1 minus the expected value of f of x t and plus t times beta eta square 2 over d sigma square. Yeah, I don't have this t. Right? All right. So now what we can do is to divide both sides by 1 over t. So on the left, we get 1 over t, the expected value of the average gradient of the entire trajectory. And on the right-hand side, we have some fx1 minus fx star. So this is the optimal solution over eta multiplied with 2. And then the last term, since I've divided both sides by since I've divided both sides by t times t times eta, so we'll get just beta and one copy of eta and d sigma square. Right. So it remains for us to find the optimal solution of the choice of eta parameter that minimizes these two terms, and we can choose that according to we can choose that according to the same rule that we've learned by balancing these two terms. So by choosing this eta to be on the order of 1 over to be on the order of 1 over square root of yeah, I'm missing a t here. Yeah, to be 1 over square root of t, then we can get this we can get the rate to be square root of t fx1 minus fx star square root and square root of d beta and then sigma square and everything inside the square root. Okay, so that's kind of bound that we get, and as we can see, this is consistent with a convergence of stochastic gradient descent in the general convex problem, right? So in some sense, in the non-convex setting, if we in addition assume smoothness, then we can get the convergence. Then we can get a convergence of the average gradient. So notice that this is larger than the smallest possible gradient that we encountered throughout the throughout the optimization. This is, yeah, so the minimum is always smaller than the average. So therefore, like this shows that the gradient descent algorithm, the stochastic gradient algorithm would have run into like a region that is sufficiently flat. Okay, so now let me state the gradient descent algorithm for differential privacy. So the algorithm is actually very straightforward. It simply add noise artificially to this gradient plus eta t and sum of the gradient of Li at theta t, right? So this is our gradient of f at theta t, right? So the noisy gradient descent algorithm simply use Gaussian mechanism to privately release this. And the point of analyzing the stochastic gradient descent rather than the gradient descent is because, like, after we add this noise, this becomes an instance of the stochastic approximation of the gradient. So we can see that if we call the whole thing gt, and we can see that this gt conditioning on theta t is equal to, the expected value is equal to gradient of f theta t. And secondly, the variance or the norm of the trace of the covariance given theta t, and this is equal to d times the sigma square. Right? It checks the condition that we have, and we can just make use of the theoretical analysis that we've done so far to analyze the convergence of the noisy gradient descent algorithm without changing anything. And the privacy analysis of this algorithm is also very straightforward because this is nothing but Gaussian mechanism. So what we can see here is that this is a composition of T Gaussian mechanism where the number of iterations T is a hyperparameter that we choose. And in addition, this sigma is a hyperparameter we choose. We've learned that one Gaussian mechanism with like, let's say that, so what is a global sensitivity of this? The global sensitivity of this algorithm is a global sensitivity of the gradient of f at theta star. So it's just the magnitude of the individual loss function, the gradient of the individual loss function, and we know exactly what it is. It is smaller than it is this L parameter, since Li is L Lipschitz, and since Li is L Lipschitz, and then yeah, we can get that the gradient is always bounded by L, right? So every single element of this summation is bounded by L. Therefore, with this global sensitivity and this amount of noise that we add, we can know that this algorithm, each iteration of this algorithm is rho z CDP. So I recall the concentrated differential privacy and Renyi differential privacy that we've learned that provides a good characterization of the Gaussian mechanism. And when with rho equal to 2 sigma square, I guess L square over 2 sigma square. And the composition of T Gaussian mechanism is simply T times rho the CDP, and this is with rho parameter being total being T times L square over 2 sigma square. And if we want to calibrate to a particular choice of this rho, and then we can see that the sigma square over T parameter is equal to L square over 2 rho total, right? So let's say we want to calibrate this Gaussian mechanism to satisfy rho total, and this is a choice of the ratio of these two hyperparameters. What is nice about this is that it depends on this sigma square over T. And if we flip this to the previous side, we can see that this sigma square over T is together in the utility analysis. So we can simply substitute this sigma square over T inside this utility analysis to obtain the right choice of to obtain the right choice of this sigma and t ratio in order for us to obtain this rho CDP parameter. And then there's our standard conversion from rho CDP to epsilon delta dp for your favorite epsilon delta. Okay, so I'm gonna stop here, and then we'll continue with more details on how to do this in the next lecture, and then we'll also see how we can interpolate between the gradient descent regime and the stochastic gradient descent regime when this noise can sometimes be very small, right? When this noise is sometimes very small, then maybe it makes sense to choose another kind of learning rate that generates faster convergence rather than just using this small learning rate that depends on this sigma parameter. Okay, and hopefully we can get the best of both worlds, and then show that this algorithm enjoys strong differential privacy and also the best possible privacy utility trade-offs that we can hope for a broader family of problems. All right, I'll stop here, and I'll see you guys on Wednesday.